Hello everyone, this is our lecture for estimation. Here are the learning objectives. This is what we're going to cover and this is what you need to know for the next proctored exam. Think of these learning objectives as your study guide for the next exam. So take a minute, hit the pause button and read through these. In this lecture video, we will explore inferential statistics. We will begin our journey into inferential statistics with estimation. We will discuss point estimates and confidence intervals. After we select a sample, we know the responses of the individuals in the sample. The reason we analyze a sample is not to learn about the individuals in our sample, but to draw from the sample data some conclusion about the wider population that the sample represents. Statistical inference provides methods for drawing conclusions about a population using sample data. Because a different sample might lead to different conclusions, we can't be sure that our conclusions are correct. Statistical inference uses the language of probability to say how trustworthy our conclusions are. The two most common types of inferences are 1, estimation, and 2, tests of significance, also known as hypothesis testing. We use estimation in 2 ways. First, with point estimates, and second, with confidence intervals. We will discuss both. Since the information collected from a sample does not contain all the information in the population, we assign probabilities to our estimates. These probabilities serve as a way to measure what will happen if we estimate the value of the parameter many times and provide a measure of confidence in our results. The goal of statistical inference is to use information obtained from a sample and generalize the results to the population that is being studied. The first step in estimating the value of an unknown parameter is to select a random sample and use the data from the sample to find a point estimate of that parameter. A point estimate is a sample statistic that estimates the value of an unknown population parameter. A point estimate is a single value that best describes the population of interest. For example, the sample mean M is an unbiased point estimate of the population mean mu. The sample standard deviation S is an unbiased point estimate of the population standard deviation sigma. The following are examples of point estimates. The number of Facebook friends among people under 30 is sample mean equal to 220 with a standard deviation of sample standard deviation of S equal to 18. The advantage of a point estimate, like the sample mean, is that it is easy to calculate and easy to understand. The disadvantage, however, is that we have no clue as to how accurate this estimate really is. In order to deal with this uncertainty, we can use an interval estimate, which provides a range of values that best describes the unknown population parameters. Why are most population values or parameters unknown? Well, the size of populations make it nearly impossible to gather that much data. Most researchers do not have the resources nor the time to gather population data. Why do you think census data is collected every 10 years? Imagine how much it would cost to collect census data every year. So, how accurate is a point estimate of the mean? A way to answer this question is to ask, how much do means from a sampling distribution vary? One indication of this variation, we know, is the standard deviation of the sampling distribution of sample means. Like any standard deviation, it tells us how much scores in the distribution typically vary. In this case, the scores are sample means. Since our interest is in making an estimate of the population mean, any variation is error. So the amount of variation is the amount we expect sample means to be off or in error as an estimate of the true unknown population mean. Remember that sample means vary from sample to sample. We know that if we take different random samples from the population of interest, we will get different sample means for each random sample. This difference is what we call sampling error. The point estimates, these sample means, would be reasonably good guesses of the population mean. But due to the variability in sample means, we are better off reporting a range or interval of values with some measure of the likelihood that the interval includes the unknown population mean. In statistics, we construct intervals for a population mean centered around a guess. The guess is the sample mean, or the point estimate of the population mean. A confidence interval for an unknown population parameter consists of a range of value. The level of confidence represents the expected proportion of intervals that will contain the parameter. The level of confidence is the proportion of times that the interval contains the population mean if repeated samples were obtained. The three most commonly used confidence levels are 90%, 95%, and 99%. The higher the level, the lower the risk that our interval does not contain the parameter. A confidence interval is a range of numbers, such as the mean number of Facebook friends is between 200 and 240. A confidence level specifies the proportion or probability that the population parameter will indeed lie within that specific range of values, such as we are 95% confident that the true population mean number of Facebook friends falls within a range of 200 to 240 friends. There is a 5% probability that the true population mean is less than 200 or greater than 240. So a 95% level of confidence implies that if 100 different confidence intervals are constructed, each based on a different sample from the sample population, we will expect 95 of the intervals to include the population parameter and 5 to not include the parameter. The most commonly used z-critical values for what we call a two-tailed test are two-tailed, we'll talk about in Chapter 8, 90% confidence level, z equal to plus or minus 1.65, a 95% confidence level, the z-critical is equal to plus or minus 1.96, and 99% confidence level, z-critical is equal to plus or minus 2.58.